Section 8.6 is representing functions as power series. So we've already been introduced to power series. That was section 8.5. Now we're considering function representations of power series. So we're moving along one more step to say, not only will we have a power series, but we'll be able to take a function and then represent it as a power series, okay, as we see given here. So this will be just a sort of a very basic way to extend power series representations of functions. And it'll all hinge from this geometric series identity that we have below. So we know that the sum from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x, provided the absolute value of x is strictly less than 1. Now, what we can do is take this identity, we can create or build several different power series, really several different families of power series, to speak even larger about it, essentially just from this, by doing operations on this identity here. So the first things we'll see will be algebraic adjustments. So in other words, what if we don't have 1 over 1 minus x? Maybe we have 1 over 2 minus x. We'll have problems where we'll be able to adjust that to have a power series representation. It's just an algebraic manipulation. And we'll see another one where it's 1 over 1 minus 3x, I believe is the next example. And those are just all algebraic substitutions to use this known identity to get to a new power series for whatever function we might have been given. So the next thing we'll do after that will be using calculus to build new power series. So we'll see that we can differentiate and integrate power series, which means we could differentiate or integrate the functions that are on the left-hand side here, and thereby create new power series from there as well. It won't be our go-to method in the future for doing so, but it is a nice set of techniques to know when dealing with power series. Okay, so use a known power series representation to find a power series representation for 1 over 1 plus 3x. That's a little different than what I stated before. So our goal is to rewrite 1 over 1 plus 3x, which already looks pretty close to the left-hand side of the identity on the previous page, this side. Because if we can rewrite it in something that looks like this form, then we can express it in a power series. So let's see that happen. We've got 1 over 1 plus 3x, and our aim is to make it look like 1 over 1 minus u. Well, this is pretty straightforward. The plus sign just becomes minus a negative, and we group that negative inside parentheses. So we've got 1 over 1 minus negative 3x. Negative 3x now plays the role of u, and we could rewrite this as 1 over 1 minus u. Well, we know that this will converge when absolute value of u is less than 1. Actually, I'm sorry, we know that its power series converges when the absolute value of u is less than 1. But we've got a key substitution to keep in mind here. So anywhere we see a u, we just put a negative 3x. And we'll do the same here. So now we know that 1 over 1 plus 3x, this is our u. U is negative 3x. So we now have negative 3x to the n replacing u. So it's that simple of a swap. We've now expressed 1 over 1 plus 3x as the sum of negative 3x to the power of n, provided, and it's a radius or its interval of convergence is given here, as negative 3x absolute value needs to be less than 1. Of course, we can do some algebraic work with that. The main thing is to actually find its radius of convergence by getting rid of this multiple in front of x. And also the simple thing is that we could just cancel that negative. That is positive in the absolute value bars. So when we solve for x in this, we have the absolute value of x is less than 1/3. Our center is 0. Our radius of convergence, where we're looking for that, is 1/3. Okay, and we've cleaned this term up a little bit, or not. We've made it a little more complicated, but we just pointed out that it's got an alternating term, and we've got 3 to the n times x to the n. This is just as well as writing this. I just really like that we split out the alternating term here just to emphasize that it is an alternating series. So that's our first one of our first techniques, algebraic manipulations. Now in other problems, this might not be a 1, this might not be a 1, and this term might not be a 1. So we'll just have to work with whatever different algebraic things we need to do in order to make this, in order to form this structure out of a given function like that. Once we've got this structure, we can express it with its through its geometric series, given this condition, and do the remaining work to clean it up. So that's a nice tactic. Other things we might be able to do to build new power series from old will be to take a given power series, say this one here with center A, coefficient C sub n. It's an infinite series from n equals 0 to infinity. And if we represent it, we say it's a function f of x is equal to this power series, or has a value equal to, or it can be represented as this power series, whichever way we want to think about it. We can take the derivative of this power series by applying the power rule to the terms of this series. So generally the way we'll think about it is we don't know what f of x is. We just know we just know it has a power series representation, which is sufficient to fully represent it. And it's actually really useful to approximate values for that function. So we can, what this is telling us down here, number one, is that we can take the derivative of that power series with respect to x. And you see what's happened is this n has become an n minus 1 with a multiple of n at each term. And that's essentially just the the derivative power rule. And we've changed the index by just a little bit, because remember that C0, C naught, is when n is equal to 0. Well, when n is equal to 0, this term is just 1 times C naught. C naught was a constant. When we took the derivative with respect to x, C naught differentiated to 0. So we lost the 0th term. So we start this series at n equals 1. It's often a little bit easier to write out the first few terms of one of these series and then differentiate. I'll do that below when we do an example. Similarly, we can integrate. So now we have n equals 0 to infinity. We gain a term. This is sort of a new C naught right here. It's just another, it's the constant of integration as we usually have it. If we have some sort of conditions that can help us determine it, then we can write it in. If not, it's just an unknown constant, just as it's always been for any indefinite integral. And we notice that we've just got the power rule for an antiderivative applied to these polynomial terms of that power series. So it's nice and straightforward. Let's see an example. So they ask us to find f prime and the antiderivative of f of x. So two different operations we need to carry out. And we're given this as our power series. It's just, well, it's just the geometric series, the sum from n equals 0 to infinity of x to the n. We know that that looks like 1 plus x squared plus x cubed. And that's for n equals 0, 1, 2, and 3, and so on. The derivative of this, we can think of it as an operation d dx on the series n equals 0 to infinity of x to the n. And what this rule really tells us up here is that in order to find the derivative of this series, it's the series of the derivatives of these terms. So in other words, this rule, in terms of operators, lets us pass d dx to the other side of the summation. That's something that you don't always get in mathematics. As much of our theorems in calculus let us do things like exchange the orders of these operators. So for functions that have power series that converge, this is fine. Okay, this exchange that we have here is completely valid. So when we take the derivative of x to the n, that's pretty much looks like that power rule right out of the textbook. N comes down as a multiple. We have x to the n minus 1. And we say that this is true for values x between -1 and 1. Or in other words, on the interval -1 to 1. So we have essentially come up with our derivative here. It's f prime of x is equal to this power series. And we've done this completely in power series notation, right? And also mind, we did take care of n equals 1. We know that that constant term in the original power series integrated to 0. And we could double check. We write down the first few terms, the first 4 terms like we did before, n equals 0 through 3. And this is literally just writing it down for each one of these. I added a 0 here for an n equals 0 case in the series, even though it's not really there, but it is just a 0. That's just a placeholder. So we see that this does make sense. And you can match the derivatives here in this line to what the derivatives of these terms would have been. And they're exactly the same. 1 differentiates to 0, x differentiates to 1, 2, or x squared to 2x, and so on. For the integral, the antiderivative of f of x with respect to x, we have the integral of the series, and then the rule above tells us we can swap these operations. We can move the integral inside, integrate that single general term, and that series of those antiderivatives will be our new series. And we've added our constant of integration over here, plus c. And that could combine, if we had, like I said, some conditions to determine constants, that could combine with our n equals 0, or sorry, our c naught term somewhere along the way. Actually, it will not, because our c naught term would be times an x. So we'll keep it exactly as it is up here. That constant is all on its own. We would determine it from some given conditions, or just leave it as c like we do here. Now, that's it, right? And we could check, let's take the antiderivative of these, and we could crank out the first 4 terms of this series as we have it, and we'll see that those in fact match. We should start with an x plus 1/2 x squared plus 1/3 x cubed, and so on. And we should see that we'll have proper antiderivatives for all of these. Okay, with that added constant c right there, which shouldn't combine with any of these, because remember, what was a constant in our original series will become an x once we integrate. Right, so that's our basic technique using calculus to build new power series. In this example, we're asked to find a power series representation of f of x equals tangent inverse of x. What we'll start with is 1/1 minus x is equal to n equals 0 to infinity of x to the n. This is our geometric series representation. The idea and the trick to this one is to recall that the derivative of tangent inverse of x is 1/1 plus x squared, or as it's written here, the integral of 1/1 plus x squared is equal to tangent inverse of x. Of course, I'm missing a plus c here for the antiderivative, the indefinite integral, but I've just chosen it to be 0 because it's going to be sufficient for us to use this identity to build a new series for tangent inverse of x. Now, what we have to realize is that 1/1 plus x is fairly similar to 1/1 minus x. Now, the way that that works is we just write this as 1 minus negative x squared. So we now have a u playing the role of, or negative x squared playing the role of u for 1/1 minus u, just as we did before in the algebraic example. So in our power series, this being a u in the original power series, negative x squared is playing that role, and we plug it in here, and we've got this power series representation of this function. Okay, what's its radius of convergence? Well, just as before, and just as the theorem of the previous example states, its radius of convergence is inherited by from the original series that we're dealing with. So in other words, if we altered this series by taking a derivative or making a algebraic substitution, well, then our radius of convergence is still the same. And this is actually written as the interval of convergence, x between -1 and 1, but it states essentially the same thing as absolute value of x less than 1. Okay, we've done one little trick to peel out the -1 to the power of n, just to demonstrate that this thing is an alternating series, just to kind of point that out. It's just a fairly conventional way to write that. And we have x squared to the n, which gave us x to the 2n, and we stuck with that. Completely sufficient way to represent this series. Now, down below, we've got to bring this closer to tangent inverse. Well, to get to tangent inverse, so now that we have this power series, if we integrate this function, we'll get tangent inverse of x. So we write that tangent inverse of x is the antiderivative of this function, or the indefinite integral of this function, and that's equal to, well, that's the integral of the power series of this function, which is this. So we've swapped that out right here, and we're ready to integrate this power series, and we remember that the integral of a power series on its interval of convergence is the power series of the integral of the general term. So we just pass the integral sign through. We do our operation on x to the 2n, our antiderivative operation. We've got x to the 2n plus 1 divided by 2n plus 1. Our alternating terms constant with respect to x, so nothing happened to it. And this is on the interval -1 to 1. One thing we can do is we can check the endpoints. We might gain an endpoint in a subsequent representation of one of these functions. If we can prove that it's convergent at one of these endpoints, well, then we've actually we can add that endpoint. So that's the one thing that might change from representation to representation. So down here, this is sort of an extra interesting aside. If you don't have time for it, you can probably scroll ahead in the video. But this is an approximation of pi. It's not a very good one, but it's just an interesting thing we can do with the function that we just built. So if we check the right endpoint and we say that x is equal to 1, well, we substitute 1 everywhere there's an x in this power series. We have 1 to the 2n plus 1. That's a very easy thing to handle. And we just end up with -1 to the n over 2n plus 1. That's from here and here. And we know that that's an alternating series, and we're interested in whether or not that thing converges. So, well, we note that its positive version, at least omitting this alternating portion, 1 over 2n plus 1, has a limit of 0 as n goes to infinity. So that's first condition checked and passed by the alternating series test. The second is to confirm that it's decreasing. When we get to this identity, we realize that this is decreasing for any n values, really. So we're set there. And we can conclude that this series converges by the alternating series test, which means that our power series can include that right endpoint of 1, which is interesting because if we can plug in 1 for x to this power series and it converges, what that tells us is that tangent inverse of 1 is equal to, well, this series right here. And well, tangent inverse of 1 is pi over 4. If we recall trigonometry, tangent inverse of 1 is pi over 4, and so that means that pi over 4 is equal to this series, -1 to the n over 2 to 2n plus 1, n equals 0 to infinity. And then lastly, well, if we solve for pi, multiply 4 by both sides using this as our equation, pi over 4 equals that series. Then we have pi equals 4 times the series, 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and this is actually an approximation of pi. So kind of an interesting thing that we can do. It's an extremely slow to converge approximation of pi, but it does in fact do it. We can see that here. We've proven it by the alternating series test, and might be one way, if we were really desperate, one way to tell a computer what pi actually is, or at least how to approximate pi for later calculating purposes. Now, our last example is to use power series a little bit more practically to help us, evaluate or at least approximate an integral. So evaluate the indefinite integral as a power series. In this case, we're just going to represent it as a power series and be happy with that. So notice this. Later on, we'll talk about further approximations of things in another exercises and examples as well. But once you can come up with this power series, approximating at a point is just a matter of plugging that point in, churning out terms of the series until you've met the degree of accuracy you're looking for. So we've got an integral here that is not really manageable through any conventional techniques. U substitution for 1 plus x wouldn't work because that doesn't get rid of this x squared. Maybe there's some algebraic tricks. One thing one might think of is put x squared in the exponent of natural log's argument since it's a multiple. Well, that looks a lot worse. So maybe that's not the way to go. And really, integrating this thing doesn't seem very doable for us. So what we want to do is we want to represent this thing as a power series so that way we can actually integrate it. To get there, we've got to take a few steps along the way. So we're kind of bringing it back a ways to say, okay, natural log of 1 plus x is equal to the antiderivative of 1 over 1 plus x. So what you might do is this. You might take the antiderivative of this function and see that it is, in fact, natural log of 1 plus x, or even better, differentiate this function and see that you get 1 over 1 plus x. Now, this is familiar to us. This 1 over 1 plus x is the function that's equal to the geometric series. So we'll do 1 over 1 minus negative x to put it in the form of the geometric series. And once we're there, we realize that this can be replaced with just swapping negative x in place of the u for 1 over 1 minus u. And we've got negative x to the power of n. And that's all been done within this integral, so that we're still equal to the natural log of 1 plus x. And what we're getting is a power series representation of natural log of 1 plus x. Now this is true for the radius of convergence that this holds for, or that our general power series, geometric series holds for. And we know that we can flip these operators, so we take the sum of the integral of the general term. Negative 1 to the n is a constant with respect to x, so it doesn't do anything, but we do have x to the n plus 1 over n plus 1. And we'll choose c equals 0 just to simplify our work. We could carry it along with us if we really wanted to and needed to bring those details, but in this case, we're just looking for a power series representation of the indefinite integral, and this is going to be sufficient because we're still going to integrate and add another constant anyway. So what we've got is that natural log of 1 plus x, which is part of our integrand, is equal to this power series. And x squared is not a particularly difficult term to manage, especially in relation to a power series. It's a polynomial term. When we multiply it by a power series, we're going to see that it just has a very easy way to accommodate it. So the integral of natural log of x squared, natural log of x squared, natural log of 1 plus x is equal to the integral of x squared times the power series representation of natural log of x. And interestingly enough, this x squared can pass inside the series because it's just going to multiply by each term in this series, and all it's going to do is raise the power of those values of x, or those x's, by 2. So instead of having x to the n plus 1, we have x to the n plus 3. And here we are ready to integrate this power series. It's nice and clean, pretty easy to do. We remember that we can just swap the series and the integral, and we just integrate the power series term, right? This is a constant with respect to x. And when we integrate this power series term, we get x to the n plus 4, and then divide by that new power of n plus 4, and that joins the n plus 1 down in the denominator. And that's it. That would be the power series representation of the integral of x squared natural log of 1 plus x. We add our constant of integration because it's an indefinite integral. So if we needed to approximate this as a definite integral, what we could now do is say, okay, for our endpoints of our integral, whatever they might have been, if they were given here and here, it's the upper endpoint minus the lower endpoint. And now we'd have two series that we could take the difference of, evaluated the upper endpoint minus the lower endpoint. Maybe we could combine their general terms for those two series. And if we could, then we just have a single series, and then we can crank out terms of that series for whatever x, as we desired for accuracy. And the approximating with numerical series, well, those x's will be set as numbers at this point. We're evaluating at the endpoints. Using that technique, we'd be able to evaluate the indefinite or the definite integral to whatever degree of accuracy we desired by just taking more and more terms until we attained it. So we'll see some of that in the next section, which is 8.7, Taylor series and Maclaurin series, where we'll learn more general techniques to build these, and we'll practice a little bit more with approximating definite integrals, approximating the values of functions with these power series, but really just starting to introduce what you could ever do with these. We won't go much further than that in the course because each of you in your own disciplines will see applications of this in the future, guaranteed. So that's it for 8.5 or 8.6, and we'll do 8.7 in the next video.